This program was brought to you by Coller Institute of Venture at Tel Aviv University.
Actually, Roy, this morning, the first presenter, gave me a great overview and a great introduction about the interaction between academic and industry and how to proceed and how to apply water technologies. So I can skip all this, and I will give you examples. I will try to reach to two examples of actually technologies, innovative technologies we developed here in Tel Aviv University dealing with industrial wastewater and hospital wastewater. The main chief scientist in this project was Professor Das Maman, sitting here, will talk after me, and myself and students of us that invested many hours in the laboratory to do this research. So, not working. Yeah. Where is the? There is a chip supposed to be here. Yeah. It's not here.
Let's start by doing this while I fix it.
Okay, no problem. So worldwide, we know today that actually, maybe I will say something before. I will take you now to a different world, to real water problems. I will take you from the marine environment to the land environment, water environment. Then we dealt with a lot of water pollution, scarcity of water, quantities, and in our group in Tel Aviv University, we are dealing mostly with water qualities, how to make the water advocate for drinking, for better agricultural irrigation, how to reuse wastewater. So the quantity of water is the quality of water is a big issue. So I will talk about these main issues as well. And today we know, I don't want to talk a lot about it, but we know that we have in drinking water, in irrigated water, best quality of effluent water. Effluent is treated wastewater. We have a lot of concentration of many compounds in a low concentration, such as pharmaceutical and pesticides, and I will talk especially on pharmaceutical residues coming from many sources. The main sources that pharmaceutical residues coming from is us, is the household. We are, by urine, release more than 90% of any consumed drug that we consumed, 90% of the active molecule we are releasing from our body. So actually the wastewater, the raw wastewater, the raw sewage contain a soup or a mixture of many compounds of many pharmaceutical that you can imagine. Unfortunately, the wastewater treatment plant here cannot sufficiently treated, even the best available technology cannot treated this compound sufficiently. So actually in the secondary and tertiary effluent that we use in agriculture, in Israel we use more than 80% free-use water for agriculture, still we have a lot of what we call nanopollutants, micropollutants, or pharmaceutical residues for many types that you can imagine. Other sources that I will talk today is coming from the industry. If I'm talking about industry, I will talk about specifically on the pharmaceutical industry. The other coming from hospital. I will hope that I will have 5 minutes briefly to give you some introduction about hospital wastewater. Our group in Tel Aviv University invested for the last 6 years a lot of effort, research effort regarding hospital wastewater, and I will talk about it later on. And today I want to give you some example on treating wastewater from pharmaceutical formulation facility, an innovative technology that we are developing and optimizing in Tel Aviv University, that ozone-based advanced oxidation process. And what is our motivation to do so? First, we want to start to engage Israel with ozone water and wastewater treatment technology because we believe that this is the future of technology. I have to emphasize that this kind of technology, the ozone-based AOP technology, is destructive technology. While we are going to break down the compound, try to achieving a non-toxic liquid afterwards, to produce a non-toxic liquid for irrigation, for drinking, for anything, instead of transfer the contaminants from the liquid phase to a solid phase like membrane does. So we are dealing here with constructive methods, the ozone-based advanced oxidation process. So what is the motivation, the big motivation? In the past, Israel mostly consumed the drinking water from the Sea of Galilee, what called Lake Kinneret in Hebrew. It was the main source of fresh water and irrigating water for irrigation, for agricultural irrigation. And we did it via our national water carrier that established in 51 years ago. You can see here from the Lake of Kinneret through the south of Israel, from the place of that we have water to the place of demand. This was actually the water system, an innovative and amazing, incredible water system that Israel achieved in the beginning of the first 20 years of when the country established. And the problem is that the Lake of Kinneret extremely characterized by high bromide concentration. So if we want to use, to oxidize the water by ozone, the reaction creates bromates, and bromates is a toxic compound. So when we are depending of high bromide water, we cannot use ozone as a technology. Recently, Israel became a bromide-free country because we have an alternative sources of water for drinking and for irrigation. So we are actually free bromide country. We are consuming less than 20% of the Lake of Galilee water, especially for drinking, some still for irrigation, but more than 80 and 85% for the 2015 and 2016 is supposed to be dependent upon desalination. Israel established for the last 10 years a few huge desalination plants. One of them is the biggest in the world, and we are supposed to produce 85% soon, 80 to 85% of our drinking water from this desalination process, and this is a bromide-free water. And especially for irrigation, as I mentioned before, using reclaimed wastewater, using high-quality effluent, secondary and tertiary effluent. Israel leading in the world for reuse and tertiary water, effluent, high-quality one for agricultural irrigation. And remember that this tertiary effluent, that is great water from any standard regulation point of view, from any traditional parameter, still we have a lot of a mixture or a soup of nano and micropollutants, pharmaceutical residues in. So we need a further technology to break down, to remove all these residues from our main source. And remember another thing, that every place in Israel that you irrigate, the agriculture, you're sitting above aquifer. Above two major aquifers in Israel. One is the coastal aquifer along all the coast of Israel, a sandy aquifer, very highly permeable, and the travel rate is rapid. And the other is the rocky aquifer along all the mountain ridge in Israel, from the north to the Negev area, to the desert area in the south. So this rocky aquifer is highly sensitive, and we are using this tertiary effluent all over. So this is the main drinking water of Israel and the main water source. So we have to protect it by getting rid from all these pharmaceutical residues. Secondly, another motivation we have in Israel, finally, I have to say, a direct approach to several major pharmaceutical firms. We have in Israel one of the biggest generic pharmaceutical company in Israel, Teva. I believe you heard the name. And when I came back to Israel from US 9 years ago, I came here and established an environmental chemistry laboratory, hydrochemistry laboratory, dealing with pharmaceutical residues. And one of the first things I did I went to the Teva and I told them, I know that there is no regulation, as Roy said before, no regulation yet. You are not required to do so, but you are the biggest, one of the biggest in the world, and you produce so many drugs. So let's do something new together. We have the knowledge of the rate of contamination. We know the rate of contamination that you cause to the environment. We have some alternative. We have some technologies. Let's cooperate together. The last 5 years was terrible. No one wants to talk with me. After 7 years, they got they had some problem with the water commissioner in Israel. Then they came and say, you know, let's work together. Then we started working together with a huge success. So we have actually this direct approach to this manufacturing and formulating facilities in Israel. After a while, we did some project even in Eastern Europe and some other formulation facilities they have in Europe. And a confident report that we got from the Israeli Water Authority said that gave us the number that increased concentration of carbamazepine, this is an epileptic and an antidepressant drug, one of the most consumed in the world, and very highly polaric and highly resistant molecule that you can find in any wastewater, any secondary, any tertiary effluent, in most groundwater reservoirs. And Teva produced these drugs a lot. And when they produce it, we found in the nearby wells, the groundwater wells, a huge concentration, highly huge concentration of this compound, and the water commissioner told them, you know, you have to do something. This is the point that they came back and said, let's work together. And this is actually enable us to apply the technologies as we want in a full-scale pilot, because both Adas and me in the laboratories invested 5 years to optimize and develop in a batch scale the technology, and when we did it with many compounds, pharmaceutical compounds, and actually we got a great result, and we said, we are ready for upscaling. One of the main problems, and if you want to know as people that coming from industry, one of the main problems for scientists like us that doing applied science is when we have a product, even it's a product or a know-how technology, at some point, we have to do upscaling. A semi-pilot or full-scale pilot, we have to upscaling. And if we are not upscaling, we can offer nothing, actually. And this is one of the most difficult point to be an applied scientist in the world, because you don't have enough grants or people from industry said, you know, do a full-scale pilot, then come back and show me that it's work. But in order to do a full scale, I need a cooperation, I need money, actually. And you know that science needs money, this kind of science needs money. And this is a big problem. Another thing that we have, another motivation that we had, that we said, okay, this is a chance to examine the polluter pays principle, actually. Because if the government of Israel, the water commissioner and the Ministry of Environment Protection told Teva, you polluted groundwater, so they have to pay for cleaning the water. They have to pay for applying or implementing any innovative technology that their scientists in Israel, a nearby university, suggested. So let's do the pilot, let's do the upscaling, let's cooperate. Let's see if you want to change the situation. And the last thing that we believe the treatment cost is not a problem because these companies are very rich. So, you know, I don't have to tell you the numbers that Teva or other generic companies earned annually. It's a huge, believe me, all of us can build many scientific institutes, energy, water, anything that you can imagine with 1 year money that they earn. So if you have a problem and you have money in your company, please invest some of the money for these technologies, apply these technologies. So the research has several questions and goals. The first question that we ask is, do manufacturing facilities present a significant source of pharmaceutical pollution? Surprisingly, no one knew, because in literature there is, I think we found 1 or 2 published papers regarding all this issue. Most of the paper dealt with pharmaceutical residues derived from human consuming and veterinary consuming, and nothing from the pharma industry. We found something in India. Remember the one paper that we found in the upper part, on the upstream of the Ganges, that one of the biggest pharma industry in India contaminated the upper part, the upstream Ganges, with we were astonished with hundreds of milligrams per liter of a drug. I can't remember the name of the drug even, but this was hundreds of milligrams per liter. This is huge, because in the environment, when we talk about pharmaceutical residues, we are talking about nanogram per liters, hundreds of nanogram per liters, up to several microgram per liters. Okay, this is a pollution. This is what we defined pollution from pharmaceutical residues. And then there we talk about hundreds of milligram per liter in the Ganges. This was incredible. So this was the first question that we asked. And the second, can we treat the wastewater on site at a reasonable cost? Because you know better than me that, and you mentioned it in the beginning of the day, that if you want to apply a technology, you have to give a reasonable cost for treatment, unless you say, okay, this works fantastic in the laboratory, but this is not effective in the real life from an economical point of view. And the goals was to determine the contribution of pharmaceutical plants to the environment drug pollution and examine the applicability of the on-site wastewater treatment. So the examined plant was a plant in the Sharon region in Israel, one of the manufacturing formulating plant of this company, pharmaceutical company in Israel. And the formulation drugs that they consumed was the carbamazepine that I just mentioned. That was, this is an anti-epileptic and even antidepressant. And the second was venlafaxine. Venlafaxine is a dual agent drug. It's dealing with anxiety and depression as well. One of the most consuming depression and anxiety molecule in the Western world. Europe, US. The generic name, I believe you heard, it's called Effexor, one of the generic names. And we found venlafaxine in microgram per liters, in groundwater, in wastewater, in effluent water. This is a highly concentrated, polluted pharmaceutical drug. And Teva produced these 2 drugs all the time. Okay? So we decided with them, actually, let's try, they had problem with these 2 drugs, let's try to see if our technology can break down totally these 2 drugs. And in the past, their non-treated wastewater discharged to the nearby local wastewater treatment plant, and you can see here the factory, and they discharge the non-treated wastewater treatment plant directly to the nearby domestic wastewater treatment plant. And because there is no in situ treatment, they had something that called a primary biological treatment, but this was a joke. Nothing happened, okay? And actually raw sewage diverted directly from the plant to the nearby wastewater treatment plant. This is a domestic one. And the load of drugs they put in this wastewater treatment plant was huge. And the first question was, do manufacturing facilities present a significant source of pollution? You can see here. This is the wastewater analysis from the domestic wastewater treatment plant that I just mentioned. And look here, the carbamazepine and venlafaxine in milligram per liters. Milligram per liters. This is an incredible, huge amount of pharmaceutical that can derived only from industrial plant, not from human, not from veterinary, only from industry. This is, you have to understand, this is I know that to say, wow, this is barely a milligram per liter, but this is called a huge amount, okay? This is an extremely amount of, so we got the answer that, let's continue here maybe, that we calculated the venlafaxine load in 2 wastewater treatment plants. One was the treated one, the nearby the Sharon River that usually dealing with 100K people, and this treated wastewater, and the wastewater number 2, this is the largest one in Israel, and if you can look here, you can see that the load that we got only from industry related to others, it's huge amounts. So we actually answered the first question, yes, the local scale manufacturing facility, a major pollution source. We got a huge amount, a huge contribution from the source, this source. The examined treatment train was to do some biological treatment, and afterwards to do a tertiary polishing with ozone-based AOP. And of course, the specific goal was to reduce the concentration of these 2 drugs. The biological treatment show nothing. So after biological treatment, there is no attenuation, there is no reduction of the compound, so we need a further tertiary treatment to do. Afterwards, we decided to do the AOP, ozone-based AOP, and when we do AOP ozone, then I have to give you one slide what AOP is. So AOP, the advanced oxidation process, is a general terminology used for any huge of many compounds process used to oxidize, mineralize any organic pollutants in water. We deal in water by process involving the acceleration of production of hydroxyl radicals, free radicals. They are very, very potent, and they are extremely reactive. Their life is very short, milliseconds. One of the problems, they are unselective, but they have a very low steady state concentration. You can see here the numbers, and you can see here the oxidation potential is the higher one. So we want to produce hydroxyl radicals in order to break down the molecule, but this AOP. During time, I'm not going to go on this process, but actually, when we talk about ozone degradation, we have direct and indirect processes. The direct process is by the ozone interact with the pollution directly, and the indirect that we are putting here more like hydrogen peroxide in order to accelerate the production of hydroxyl radicals, and then we can attack the hydroxyl radical can attack the pollutants and create a better product. Okay? Of course, in influent, we have a little bit more complicated issue, because in influent we have organic matter that can be a scavenger and can consume, because these hydroxyl radical are not selective, remember? I cannot tell this OH to say, go directly to the carbamazepine, skip the organic matter. So I have to deal with all this natural organic matter that I have in the water, in the solution, and I have to optimize the system, and we optimize the system many times in our laboratory. The results show, actually, interesting results. CBZ, you see here, removed in 99%. The VLX removed in 98%. The O3 treatment, the ozone treatment, significantly degraded both compounds. You can see here that the VLX, the venlafaxine, degraded a little bit slower due to a lower KO3 reaction constant. You can see here the differences in one order of magnitude. This is explained the difference, 99%, 98%. And both compounds are fit actually to the common acceptable values up to 1 milligram ozone to 1 milligram DOC, because we have a lot of dissolved organic carbon in the water, so that we have to optimize the amount of ozone we have to inject to the solution. Usually in the literature or in the industry, it's acceptable to use 1 milligram ozone to 1 milligram DOC. So if I have 10 DOC, I will inject 10 milligram ozone in order to do a good job, okay? So we wanted to know if we have here, we wanted to actually to differ between direct and non-direct degradation product. process. If we have a direct degradation through ozone only or by radicals. To do so, we use PCBA. This compound knows to degrade only the OH radicals, okay? And not the O3, not the ozone, that cause direct degradation. Consequently, actually served as an indicator to the presence of OH radicals. And you can see here the results. You can see here no change. Stable PCBA demonstrate no OH radical involved, saying that only direct degradation by ozone occurred. And this is what we got. In municipal wastewater, these drugs degraded up to 50%, more OH radicals involved. In pharmaceutical plant wastewater, high concentration of scavengers, we have a lot of acetone. This scavenger actually consumed the OH radical, was a scavenger. They consumed most of the OH radical, so creating only direct degradation by O3, okay? Degradation product. One of the main things that you have to understand today in water technology issues, if you're going to break down compounds, it's not enough to say, you know, I have a technology that knows how to break down all the compounds you want. And we talk about compounds, we talk about parent compounds, the known compounds, okay, that they have names and structures and chemical characterization and anything. But what about byproducts, metabolites, degradation products that I could produce? Some of them even can be more toxic than the parent compound. Some of them could be potent, some of them could be bioactive. And we invested a lot in our laboratory the last 5 years in order to understand the degradation process under environmental condition and under ozone-based AOP in order to understand which compound, which degradation product we obtained actually, and if the toxicity of them. The result's supposed to be a non-toxic solution. If we have a toxic solution, then the raw one, we are in a bad solution. Even though we are destroying 99% or 100% of the parent compound, if the result is a more toxic liquid, this is wrong. So today we have to demonstrate that our technology even make the solution, the product water, better, non-toxic. So we can see here that we found some degradation products. I have no time to talk about all of them, but we found out that we have to do some additional biological treatment after ozonation in order to get rid of the degradation product. And to do so, we actually measured the BOD in order to understand the biodegradability of the compound, because if we are going to put back this solution after first ozone treatment to biological treatment, we want the bacteria to do a better job. And to do a better job, in order to do a better job, I have to increase the biodegradability of the compounds. Meaning that I have to, by the ozone, chopping the big molecules, chopping to small molecules, and then by this I'm increasing the biodegradability. I make the solution easier for bacteria, for specific bacteria, to degrade them biologically, and then I will get rid from even from the degradation product. And we examine all this, and we found that we increases dramatically the biodegradability of the solution, and we actually giving back to the biological treatment a smaller chopped dissolved organic matter, including the degradation product that we produced, for easier degradation by bacteria. The question number 2 was, can we treat this wastewater on site in reasonable cost? We did some calculation. I don't have time, unfortunately, to get into calculation, but you can see here that after a while we get to $0.42 for cubic meters, and this is quite cheap, actually. And we found out that even when we are increasing the biodegradability and we are doing another cycle of biological treatment, let's say that after this treatment, we can release this product, this water, to the domestic wastewater. Again, in order to do all the secondary treatment again, we can make this treatment even cheaper. So we can treat in reasonable cost. I want to summarize this part, and I need only 5 minutes to do a brief summary of hospital wastewater. Wastewater from pharmaceutical manufacturing facility can cause actually significant local drug pollution. We found out the biological process followed by ozonation efficiently reduced the concentration of these drugs. And different ozonation byproducts were identified, and we found that they are likely more biodegradable than the parent compound, and thus a subsequent biological treatment is recommended to chop them totally. Treating manufacturing wastewater on site is relatively costly. However, it can reduce local environment load drag. The polluter should pay. The second, really briefly, only to give the idea, is the removal of pharmaceutical from hospital wastewater using this advanced oxidation process. And I want to characterize hospital wastewater in 1 minute. Hospital wastewater, as you can imagine, contain toxic, mutagenic, persistent, can use more words, and highly concentrated chemicals and as pharmaceuticals for many difficult toxic pharmaceutical. These compounds, we know that some of them can cause adverse effect even to any ecosystem and even to human. And surprisingly, hospital wastewater are not considered as industrial wastewater worldwide. No country considered hospital wastewater as industrial, meaning that not pre-treatment is required. So hospital wastewater legally can discharge the wastewater, the raw wastewater, the toxic raw wastewater, directly to the nearby solution. Could be the nearby stream river, could be the nearby shoreline, could be a nearby wastewater treatment plant, could be any solution. So actually an insufficient removal of this contaminant does occur, and existing BOT treatment are far from providing the answer. Therefore, we suggest a specific innovative in situ treatment of hospital wastewater. And we actually planned a container-sized facility, including the biological treatment inside, and in situ, we can treat the wastewater and afterwards release it to the environment, release it to the wastewater as a tertiary treatment, as a free pharmaceutical compound. In this case, you know, today hospitals is not one big building with several wards of each ward in a different floor. Today it's a campus. We have many buildings. Hospital is a big campus. So we are not suggesting treating hospital wastewater in all the wastewater. We don't need the laundry, we don't need the kitchen, we need specific wards. Like, let's start with the chemotherapeutic oncology department or ward. And in Tel Aviv, we have one of the biggest hospitals in Israel and in the world, Tel Shomer Hospital. And lately, Adas and myself, with our student, we established a upscaling project. We build our technology in nearby the oncology building, dealing with a huge amount of chemotherapeutic drugs released daily from this building. And we're talking about carboplatin, cisplatin, chloroplatin, all these kind of degradation product, and cyclophosphamide, a lot of toxic chemotherapeutic drugs. And our technology taking all the sewage from this building, going through our MBR biological treatment, and then our AOP, and you can see here the building, we're diverting the wastewater from the municipal one, going through our container, after going through a preliminary secondary treatment, MBR treatment, and then after the membrane bioreactor, we have this AOP, based ozone AOP treatment, producing free pharmaceutical, a better solution compound, getting rid from all these toxic solutions. I know that I'm getting bad highs from you, so I'm finishing. Thank you very much.
This program was brought to you by Coller Institute of Venture at Tel Aviv University.